The reaction produces harmful chromium-3 oxide, so we must do the reaction under the fume hood, and we covered the bottom with aluminum foil for easy cleanup and heat protection. The only materials we needed besides the foil are the ammonium dichromate, which is our reactant, and a flame to provide the activation energy needed for the reactant to decompose. Then we placed the ammonium dichromate in a small pile on the aluminum foil. At first we tried using a match, but it was clearly not enough to light the reactant. So we turned up the heat and used the blowtorch. After numerous seconds of using the blowtorch on the small amount of ammonium dichromate, the reaction began to occur violently on its own, and the torch could be removed. As the reaction proceeds, solid chromium-3 oxide is produced and forms a volcano shape around the flame.
Snapchat this, you guys!
We then perform the reaction with more ammonium dichromate than before, and also in the dark. We then carefully cleaned up and disposed of the chromium-3 oxide. Dylan, I made sure to wear gloves because chromium-3 oxide can irritate the skin.
Our reaction consisted of solid ammonium dichromate decomposition into solid chromium-3 oxide, nitrogen gas, and gaseous water. We can see this decomposition in the formation of our miniature volcano, which was made up of chromium-3 oxide. Decomposition is a type of reaction in which the reactant breaks down or decomposes into its component parts. This can be represented by a simple diagram in which we can see the molecule breaks into its individual elements. In our demo, the ammonium dichromate decomposes and releases heat, which means that heat is a product. We see this release of heat as a violent flame coming from the pile of ammonium dichromate. In any reaction, when heat is released, heat is a product, which means that the change in enthalpy is negative. This is denoted as delta H. The change in enthalpy tells us about the transfer of energy. When the change in enthalpy is negative, the reaction is exothermic, which means energy is transferred from the reaction to the surroundings. We can illustrate the general trends in exothermic reactions in the form of energy diagrams. Energy diagrams have a vertical axis of potential energy in units of kilojoules or joules, and a horizontal axis of time in any unit. During an exothermic reaction, the potential energy of the reactants is higher than the potential energy of the products. The difference in these two potential energies represents the change in enthalpy, and we can see that in an exothermic reaction, the change in enthalpy is negative. The reaction also requires a certain amount of energy to start. In our reaction, this was the blowtorch, and in the graph, this activation energy is represented in the difference between the reactants and the top of the curve. Some reactions use catalysts which speed up reactions. The red line represents the change in the pathway when a catalyst is used. Catalysts speed up reactions by lowering the activation energy.